Hello everyone. Worksheet Bonding Inquiry Part 2. Okay, this one will be a little bit more about covalent compounds. All right, but let's read here. The octet rule states that an atom wants to have a full valence shell with 8 electrons. The number of valence electrons can be identified by examining the group number in which the element belongs. When the valence shell of an atom isn't full, the atom will gain or lose electrons, becoming an ion to fulfill this need. A general rule that exists is that metals lose valence electrons and form cations, while nonmetals typically gain electrons and form anions. All right, we have to fill in this chart. It'd be very useful to have a periodic table handy to look up all these elements. For example, francium already filled out for us here. Let's fill out for chlorine, dot structure. Chlorine is Cl, and it's a halogen, second to last column, so it should have 7 dots. It's way over on the right-hand side. It's a non-metal. Non-metals become anions, negative. Chlorine will become, now how do we know? We could take a look at the periodic table. It's going to gain 1 electron, but also on the periodic table it indicates right here that it's going to be a -1 ion, and it will gain 1 electron. -1. Now you can write that as -1 or 1 minus, it really doesn't matter. Sodium, Na. Na is an alkali metal on the first column, 1 dot. It's a metal, likely to lose that 1 electron and become a cation, in which case then Na plus 1. Na plus 1. All right, beryllium. Where's beryllium on the periodic table? Beryllium is right here, number 4. Beryllium's number 4. Symbol is Be, and it's an alkaline earth metal. We'll give it 2 dots. 2 dots. Of course, it's a metal. Metals turn into cations, and beryllium is going to be a +2 charge. Lose those 2 electrons. Silicon. It's on the far right side. It's a non-metal. Non-metal silicon is right underneath carbon. And notice that it makes a 4+ charge there, 4+ charge. All right, so we are going to say that silicon is going to make a cation, and become a 4+ charge. Silicon, 4+. Can lose those 4 electrons. We forgot to write those in. 4 and there. All right, next we have neon. Neon is a noble gas. 8 valence electrons. 8 valence electrons. And is it a metal or a non-metal? Well, we could probably say it's a non-metal, being on the right side of the zigzag. And it's not going to make any ions. Don't make ions. All right, we'll just say no for that. All right, the rest of that I'll let you fill in there. All right, let's take a look at page 2. Covalent bonds. Covalent bonds formed by sharing electrons, allowing both to have a full valence shell, occurs generally between 2 nonmetals. And here are some examples: O2, CO2, C2H6, etc. What makes them special? What are their properties? All right, now 2 nonmetals bonded together. All right, they're relatively weak bonds, usually a gas or a liquid at room temperature, but can also be solids. Does not conduct electricity in solution. They generally have low melting points and low boiling points. They're soluble in alcohol, but insoluble in water. All right, diatomic molecules. Now, we did talk about this once already. Those are the Brinkelhoffs. Remember that? They are certain elements that like to bond with each other, and in so doing, obtain an octet by doing that. Now, we often list them in this order just to kind of help us remember which elements do this. Some of them are halogens, chlorine, bromine, iodine, and fluorine, and they make diatomic molecules. Now, if we were to draw a dot diagram for them, it might look like two octets, the fluorine sharing each one of their electrons with the other one. And all halogens are going to do that similar kind of thing. Now, other ones here would be like hydrogen is one of them, and hydrogen is H with one dot, and if I have two of them, they can share their one valence electron and become a diatomic molecule, H2. And then there's oxygen. Which normally would have 6 valence electrons. So another oxygen could then share valence electrons, and they would bond together, making a diatomic molecule with 12 electrons shared, and two pairs shared between each other. And then there's nitrogen, which ends up making, nitrogen normally would have 5, and another nitrogen then, or I better make a little room here, another nitrogen is going to share its loner electrons with the other one too as well, and they end up making 3 shared pairs between the two of them. A triple bond. And then they have a couple of lone pairs on the outside too. Nitrogen, N2. All right, let's look again at how this all works. Either single, double, or triple bonds. A single bond is a single shared pair of electrons. Make them as 2 dots in there. Now, sometimes we have molecules that share 2 pair of electrons, and that was like our carbon dioxide that we looked at yesterday, where in between the oxygen, let me draw it with dots first here. We have the carbon double bonded to an O, which has some lone pairs, double bonded to an O with a couple lone pairs. All right, a double bond, 2 shared pairs between them. That's your carbon dioxide molecule. Now, there's another way that sometimes we draw this. Rather than drawing dots in between, we can draw dashes. Now, what does a dash represent? A dash is the same thing as 1 shared pair. All right, so if we draw it like that, it's exactly the same thing. And then we still put the lone pairs on the outside, indicating that. It's just a little bit different way to draw these kind of diagrams with dashes as shared pairs instead of a pair of dots. And then there's that nitrogen again with its triple bond, and then we can do it with 3 dashes as well, a triple bond. All right, let's practice drawing a few more of these dot diagrams here. We got a little chart. All right, we did this one yesterday. Ammonia, NH3. All right. Now, the first nonmetal in there is nitrogen, and it would have 5 dots to it. All right. The hydrogen, which has 3 of them, they each have 1 dot. All right. And we need to have 3 hydrogens for every one of these molecules. All right. Now, we could start with the nitrogen, and then we could add in the hydrogen. Remember yesterday we did it with a blue dot, so I'm going to do that. I'll put the hydrogen here with its electron, another hydrogen here, and another one here, each bringing in its one electron that is shared. All right, if we do this structural formula, that's when we use dashes. Instead, we could, as N with a dash to the H, a dash to the H, a dash to the H, and then a lone pair on there. All right, that might be a different way to draw it. All right, let's continue. Molecule hydrochloric acid, HCl. Now, we talked about this before. Hydrochloric acid, that's regular stomach acid, as well as other acids you can find out there. Lewis dot structure, okay, for the nonmetal, chlorine, a halogen, 7 dots, unpaired electrons. Well, we should actually leave that until we're done with drawing the structure of it. The other one is hydrogen, H, which it's one valence electron. And the question, how many hydrogen atoms need to bond one chlorine atom to form a stable molecule? Well, it's one of each. We got the formula there already. All right, let's draw what this will look like here. We have a chlorine with 7 dots. All right, and then we have a loner there. So then the hydrogen can come in and connect onto that spot with its one valence electron, make a shared pair. All right, if we do it with the dash, then we can do Cl dash to the H, and then it still has these unshared pairs. So we have unshared pairs. In the chlorine has 3 and the hydrogen 0. All right, let's look at this one, carbon dioxide again. All right, we already did this one a couple times now. All right, we got carbon with 4 dots, and then we have oxygen, O with 6 dots, and we're going to need 2 of them in the formula there. Let's just jump right down to drawing the dot diagram for it. Carbon, 4 dots. Hook on an oxygen. Well, let's hook one right here. And I'm going to make oxygen's dots blue. Or I'll change that up here too. They're going to be blue so we can see where they go. One gets shared, one is not shared. Another oxygen comes over another side with its loner, couple of pairs, and another loner. Remember then that these loners are going to come in and be a shared pair, and same thing on the other side, come in and be a shared pair. That will end up then looking like this, and having 2 shared pairs in between. All right, now if we do it with the dashes, we got 2 dashes for the double, and then those lone pairs are still out there for the oxygen. 2 dashes to the oxygen, and some lone pairs out there as well. All right, we could draw it like that too. All right, let's do one more chart here, and then we'll just do a few more. Iodine, I2. All right, that's one of those Brinkelhoffs. I has 7 dots normally, and the other one has also 7 dots. So these two are going to hook together to make up I, 2 octets everywhere. 1 shared pair in between. 1 shared pair. We could say I dash to I, and then loners on the outside. All right, let's try a few more dot diagrams here. A few more dot diagrams. All right, now if we got one element, P, and three BRs, then probably that one element's going to be in the middle. All right, first thing we got to do is look it up on the periodic table. Phosphorus is P. All right, that's in the column that has 3, 4, 5 valence electrons. So let's put that in the middle. P, 5 valence electrons. 5 valence electrons. All right, can be very similar to nitrogen. And then Br has 7. So those 3 BRs will connect on, well, let's make them blue so we know whose is whose here. Share 1, and then have a bunch on the outside. All right, on the bottom. Br, share 1, have a bunch more on the outside. And one more then on the top. Share 1 electron, the rest on the outside. All right. Each element then gains its octet. All right. B, O, F2. O, F2. All right. O should have 6 dots, and F should have 7 dots. OF2. All right, let's start by putting the oxygen in there. And oxygens have 6. Fluorine, halogen should have 7. Maybe we should make those blue again. Like that, blue. So we're going to have 1 fluorine with its loner shared, and then its unshared pairs on the outside. The other fluorine, F2, will be 1 shared pair and the rest on the outside. All right, there we go. H2O, we did that one already. H2O. All right, we have H's with 1 dot, O's with 6 dots. Let's start by putting the O in the middle with its dots. We'll make those red. And the hydrogen is going to hook on the outside with its 1 dot to share, and another hydrogen with its 1 dot to share. Water, H2O. All right, D, there's our N2. Brinkelhoff. N's have 5 dots. 2 of them are going to hook together. So if I draw 1, and another one, we have a shared pair in the middle, and some loners on the outside. All right, again, we don't have an octet. So what would happen is that some of these loner electrons will come in and become a shared pair. Another one over here come in and become a shared pair, in which case then we end up with nitrogen with 3 shared pairs and a couple loners on the outside. All right, nitrogen, N2. All right, let's see if we can figure out SO2. All right, now what's S going to be? S is in the 876 column, the column with 6 dots, and O is in that same column with 6 dots. All right, so we have S's with 6 dots, and we have O with 6 dots. Now, if we put these two things together, the S can share an electron. All right, this might be one of those cases we have to do a double bond. We have to have 2 O's in here, 2 O's. So if we take 1 oxygen and put it onto the sulfur on one side where it could share. Then we'll put an oxygen over here with a loner, and then 2 unshared pairs, another loner. Another oxygen, we'll put it down here. Share 1, 2 lone pairs, and an unshared pair there. And we're done, except not everything has an octet. The oxygens don't. The sulfur does. The oxygens don't. So how can we solve that problem? All right, this one is a little tricky in that what might happen here is that these loners could come in and become a shared pair somewhere, like that. All right. However, if we do that, sulfur will end up with too many dots. All right, but we could shift some dots around. All right, let's say that the 2 on the right side of the sulfur will go down to the oxygen. So the 2 that were on the right side of sulfur now can be down here, and then on the other side we have 2 shared pairs, and the oxygen. Here, let me erase that there so I can put the oxygen right here. Oxygen here, and it's got the loners up above on the left, and it has a shared pair. All right, there we go. That is our solution. All right, that we have right there. We have an octet around oxygen, we have an octet around sulfur, and we have an octet around oxygen. So between one side, the oxygen is double bonded, on the other side, it is not. All right, sulfur dioxide. A little bit on the tricky side, that one. All right, silicon SiCl4, SiCl4. All right, Si, same as carbon, 4 dots. Chlorine, halogen, so 7 dots. All right, and we got 4 spots where it have to bond together. That singleton on the chlorine can match up with the singleton on the sulfur or the silicon, and we would have Cl with an octet. We'll have another Cl, share 1, unshared ones, and another Cl, shared 1, unshared ones. And I think we're supposed to have a dot on the side of silicon. Nope, we had to have another chlorine in there. That's what we needed. Another chlorine. Cl4. All right, got a couple more to go. F2O. F, halogen. 7 dots. O, 6 dots. All right, now maybe we start with the O as sort of a central thing, and then hook on that. Fluorine has only a singleton there, so it could come in and share that singleton and make a pair, and then have dots on the outside still. And we need 2 of those. So another fluorine with its singleton can share it, and then having the unshared pairs on the outside. F2O. All right, S and O. Now, if we look on the periodic table, S is right underneath oxygen, and they both have 6 dots. All right, let's see what we're working with here, though. All right, so sulfur, 1, 2, 3, 4, 5, 6. All right, there's your sulfur. And then oxygen has also 6. 1, 2, Let's do them in blue here so we can see what's going on. Also has 6. All right, now these things can bond to each other. All right, that's all we got. Bond to each other. So the loners, if we take this one shared pair, maybe just come out here and be a non-shared pair. In which case then our final drawing will look like, oops, need that blue, oxygen, like this. All right, sulfur started off with 6, oxygen started off with 6, that's 12, and how many do we have? 2, 4, 6, 8, 10, 12. All right, there we go. Double bond between sulfur and oxygen. We call that sulfur monoxide. Sulfur monoxide. All right, we got one left. Fluorine, halogen, 7 dots. It's one of the Brinkelhoffs. So another fluorine with 7 dots. Can come in. One shared pair. Diatomic gas. All right, maybe we should circle our final answers. There's F2, SO, F2O, silicon tetrachloride, sulfur dioxide, N2, N2, and the rest H2O, O, F2, P, Br3. All right, that's it. There we go. We can Dropbox.